We are going to begin with the session Streaming More for Less with Apache Kafka by Paul Brebner, who is a technology evangelist of NetApp InstaCluster. Please join me in welcoming Paul.
Thank you very much for the introduction. Let's find the right spot to stand over here so I can see the screen. That helps, doesn't it? So thank you to the FOSSASIA organisers for inviting me back yet again. I think this is about the third or fourth event that I've spoken at. Last year in Hanoi I spoke about all the open source technologies that I have used recently, which was about 30. This talk is going in the opposite direction. It's a lot more single technology focused on Apache Kafka and a new feature on Kafka as well. So I think this is it's also great to be back in Bangkok. I think it was 20 years ago that I was last here on the way back from London to Australia. So I'm based in Canberra in Australia, so it's a good opportunity to escape Australia to a very interesting part of the world. So thanks for having me. Hopefully I can work out which buttons here to push without pushing the eject button or the exploding button. So this is the story for today's talk. Kafka was simple, but streams are infinite, at least in theory. We'll look at some use cases that actually can use older data, and then looking at the Kafka tiered storage, which is the new feature, and then have a look at some practical aspects, including performance and sizing. So this is sort of everything I know about Kafka tiered storage in 20-something minutes. So it's going to be quite fast. There will also be a lot of simplification, so don't believe everything I say. Check out my blogs for the actual details if you want to try this out yourself. So Kafka was, once upon a time, fairly simple. It was just a homogeneous cluster with identical brokers with local CPU and storage. Each broker is identical. This gives you scale, reliability, durability, and availability, and simplicity at one level too. You can add extra brokers for more CPU and storage, but you have to add both at once. There's no way of getting either CPU or storage. So this is the last time I'm going to talk about the Kafka cluster. From now on, I'm going to simplify it to imagining that we're talking about just a single broker and topic. In reality, though, just keep in mind there are always multiple brokers, topics, partitions, and replication going on behind the scenes as well. So Kafka was simple. Records are sent from producers to consumers. It's basically just a pub-sub middleware system. There's an end-to-end guarantee of delivery of records in close to real time. So a record is sent from Kafka from a producer via Kafka, and when the consumers poll Kafka, they eventually get the record. For subscribed consumers, records are delivered in close to real time. There's a guaranteed delivery and guaranteed order as well. So we'll add a few more complications. So first of all, you can have multiple consumer groups, which gives you fan out of records or duplication of records. Multiple consumer groups receive each record. How does it do that? How do they do that? Well, Kafka, unlike other sort of messaging type systems, does not delete the records immediately that they are delivered, so records can be consumed multiple times. So yeah, records are not deleted on delivery. Records are initially retained in a broker cache, which is called the active segment in memory. But conceptually, streams are infinite, and here's a picture I took last year from the outback of Australia of the Milky Way. A lot of cultures, including Aboriginal people, believe that this is essentially an infinite river of stars. So this is really, in theory, at least how data streams work as well. But how do you fit infinite records in memory? Well, you can't, obviously. Memory is finite, so you have to do the most obvious thing, which is to move the data to the local disk. So records are moved to a local disk when the active segment is full. And again, a simplification is that I'm assuming that they're sent or moved one at a time. They're actually sent in sort of chunks, which is the size of the segment. And this gives you more room in memory for new records to come along. So time and space, more time in records means that older records are available for consumption, but more records will take up more and more disk space. So let's have a look at the question of when are older records consumed? So we'll look at some consumer use cases. Here you have to use your imagination. This was PowerPoint. It's been turned into PDF, and my little video of the clock going backwards does not work. So just imagine the hand going backwards here. Okay, so why consume old records? Well, essentially in Kafka, it's the consumers that decide which records to read. You can either decide to read the latest record, or you can read from specific offsets or times. So there's a whole bunch of use cases that we'll just briefly look at, which gives us motivation for consuming older records. So first of all, the sort of default consumer use case is consumption in real time. Real-time consumers subscribe to the latest records and keep up with the processing. So essentially, they just are reading the most recent records all the time. However, there are some cases where consumers can get behind, and these are called slow consumers. This is often due to insufficient resources on the consumer side, insufficient partitions, or potentially even long processing times. You may have CPU or other intensive tasks to do. Or have a dependency on some slow external system as well. So you get slow consumers, which can be a problem. Delayed consumers are slow and get behind in processing, so they may start reading from the disk if they get too far behind. And I think if I can, yeah, there's a little laser pointer indicating that essentially it's up to record 2 rather than record 3 in this case. And one of the main superpowers of Kafka that I like is it can act as a buffer. Kafka can absorb or buffer very large amounts of data for reasonable periods of time. And a previous project I worked on shows an example here. The orange line is the ability of the consumers to keep up, and the blue line shows the very large load spike that Kafka itself can absorb briefly, allowing the consumers to keep processing at the slower rate. But this causes a backlog of records waiting to be consumed. So lots of new records coming into the system can also cause the consumer to get behind. So it's a bit like a traffic jam in that case. Another use case is disconnected consumers. If the consumers come and go, essentially, they may still want to process all the records. They may not want to miss out on some of them. So they will also have to start reading from disk from the older records. New consumers. So consumers may have just subscribed for the first time to Kafka. So that you can choose then, they may want to start reading from the latest, or in some cases they may actually want to start reading from older records. But of course that will take time to catch up to the latest record as well. So another sort of superpower that Kafka has, which is really quite useful, which ties into the tiered storage story quite well, is the ability of Kafka to replay data. So some sub-use cases that I'd like to highlight here are reprocessing, replication, and migration. So first of all, reprocessing. So replaying records with, say, a Kafka Streams application to fix bugs perhaps, or add new functionality to the data is one case where you may want to replay or reprocess quite a lot of older data. Replication is another use case. Geo-replication is a particular example that we see occasionally, particularly using something like Mirror Maker, which is the Kafka technology to replicate data from one Kafka cluster to another Kafka cluster, which often may be in different geolocations. And the final use case is migration to new systems. So for example, you might use Kafka Connect to migrate data to a new sync system. So you might connect a new OpenSearch cluster to Kafka via Kafka Connect and migrate all the records to OpenSearch for subsequent processing. So all these consumer replaying use cases essentially allow consumers to replay records from the past. In common with these is the requirement to have more and older records, which means you need more storage space. So bring on Kafka tiered storage. So let's have a look at basically how it works. So this is the new feature. It's really a new architecture for Kafka rather than a feature, I think. It's remote storage in the cloud. So it essentially answers the question, what if you want lots more storage or cheaper storage or both? then the obvious solution these days is to use cloud-native storage. This gives you infinite, cheap, remote cloud storage. But how does it work, and how well does it work? So this is the tiered storage architecture at a very high level. Essentially, there are extra copies of the record stored remotely. So the fundamental Kafka architecture is multiple brokers and replication factor number of copies of the record stored locally, initially in cache in the active segment. That's number one up here. And then the second part of the data flow is when they're then moved into local storage here. And then the third new Kafka tiered storage mechanism is when the records are also written to remote storage, for example, AWS S3. This gives you the ability to retain the records for different amounts of time as well. Older records, in this case 0 and 1, are deleted from the local storage but still available in the remote storage. So the records are retained for a shorter amount of time, typically on disk. There's a new configuration called local retention, which is normally less now than the remote retention time. And on the cloud storage, the remote records are retained for a longer time than on the local storage. Oops. Yeah, okay. So one question I asked myself a few months ago trying to understand how Kafka tiered storage works was, well, if it's tiered storage, surely it works a bit like a tiered fountain. So how does a tiered fountain work? Well, basically there's two storage layers. There's the top of the fountain and the bottom of the fountain. The water comes in at the top here. So I'm using the duck here to symbolize the oldest record. So keep an eye on the duck and see where it goes. So the records flow into the system. They're put into the local storage. The local storage starts filling up and finally overflows. And when it overflows, the records are moved into the remote storage, which eventually could overflow as well, and then they are just deleted. So is that the way that Kafka tiered storage works? Well, if it was working that way, you would expect that there would be no time overlap of the records in the local and the remote storage, but there is. So that's actually not the way that Kafka tiered storage works. So just forget that story. It's not particularly helpful or accurate. A better story or an explanation is that Kafka tiered storage is more like a dam. The water and records are quickly copied to remote storage. They are deleted when the local time limit is exceeded. And the better part of the story really is that it's more like a pumped hydro system. There's an upper and a lower reservoir. Records are read from the local storage, else from the remote storage, essentially being pumped back up. Else, if they're not available there, then there's just an error at that point. So let's have a look at the duck again. Here's the upper and lower reservoir in the pumped storage system. The records come in. I'll just go back to there just to point this out. They're not immediately copied into the remote storage. They have to be closed first. So there is a small amount of data that's actually still in memory on the Kafka brokers. So the open segments are not copied. They're just available on the local brokers. However, once the records become eligible or they're closed, they are then copied to the remote storage. And from this point on, there's actually two copies of some of the records. You'll notice the duck is in both the upper and lower reservoirs. While the records are available in the local storage, the reads are served from the local storage. And eventually, the local storage fills up. And once the local storage time threshold is up, they are deleted. So those records just are not available anymore to be served from the local storage, but you will see that the records are still available in the remote storage. So this is sort of the pumped hydro model that I've superimposed on here again. So the reads for older records are served then from the remote storage while they're still available. And eventually the time is up on the remote storage as well, and the records are then deleted in the remote storage. I've redrawn that diagram just to show the time overlap. So while the data is available locally, the reads are served from the local storage, but there is quite a big time overlap with records available also in the remote storage, and then eventually some records are only available in the remote storage. and that's where they're served from, and then finally they're deleted as well from the remote storage. So it's a bit more complicated than the original default. Very homogeneous Kafka cluster, but it does give you this extra ability to store more data. In practice, let's have a look how it actually works. This is the architecture diagram that the KIP actually talks about. So there's a few more components that have to be added to make it all work. In fact, there were quite a few changes. There are changes around error handling, the fact that you're dealing with remote storage, which may have increased latency and fault behaviors. It has to also be changed to enable the consumers to not actually have any knowledge of the fact that they're dealing with tiered storage. So the consumers, from the consumer point of view, all of this is just magic and invisible. So a couple of months ago, I actually had a go at using our Kafka tiered storage on our managed Kafka that we provide. And I discovered that first of all, you need a Kafka cluster with tiered storage set up. So we provide one of those using AWS S3 as the backing storage. You have to actually create the S3 bucket in AWS and provide that information to Kafka. Then you actually have to enable the tiered storage for the cluster, and then you have to enable tiered storage for every topic as well. So you also then have to specify the local retention.millisecond time, which is the new configuration, which should probably be less than the retention.ms value, which is the original default retention time, but it's now the retention time for the remote storage. And then you write data to your topic, and then the interesting thing perhaps is that you have to wait a bit, and depending on the segment size, the number of petitions, etc., the data will eventually appear in S3. So another aspect of Kafka tiered storage and practice is performance. So it's good to notice that the producer write latency is not impacted by tiered storage. This is because the copying to tiered storage is done behind the scenes asynchronously. Things to watch out for: tiered storage writes use more Kafka cluster resources, about 10% extra CPU. So you may need 10% more CPU on your cluster. Copying and deletion to tiered storage does actually take time. Both are lazy and asynchronous. And the slightly bad, reading from tiered storage is actually a bit slower. There's a higher latency and the throughput is impacted. Records from tiered storage don't seem to be cached, so a second read is still slow as well. It's not sped up at all. And you may need more petitions, consumers, and cluster resources, including extra brokers, potentially to increase the tiered storage read throughput. And the whole system is pretty sensitive to segment size. Just some performance results we got. Consumer throughput was 3.2 million records a second, local compared to 1.2 million records a second reading from the remote storage. So yep, it's a bit reduced throughput. Latency increases from 5 milliseconds on the local to 20 milliseconds on the remote. And yeah, the blue graph shows the impact of small segment sizes. There's quite a few things you can tune, so I didn't try tuning absolutely everything. Thank you, 5 minutes, okay. So another question I asked myself was, does a Kafka cluster with tiered storage enabled have to be bigger, and by how much and for what? So my background is actually performance prediction and modeling, so I thought, well, let's build a simple performance model of Kafka and then add in the tiered storage aspect and see what we can learn. So I built a simple sizing calculator. This is a Sankey diagram to visualize what the model is trying to do. It takes into account producer workloads and computes the I/O and network in megabytes a second. And this is an example for tiered storage enabled using local SSDs for the local storage. I also produced a JavaScript model. You can find it at that link there on GitHub. This is what it looks like. It's pretty simple. Still, it hasn't been validated, so let's watch out. It's a best guess based on our knowledge of how Kafka works and some benchmarking of the tiered storage. It predicts I/O network and terabytes a month of data, and the cost for AWS S3 in particular. So some of the results from that calculator show the overhead of tiered storage compared to local storage. It's about 11% increase in I/O that's required and about 33% increase in network capacity. Including EBS in the mix as well. So a lot of people actually do run EBS as local storage. You see there's a few differences. The main difference is that EBS is a lot more network heavy, so you see a big increase in the network demand, and that has an impact on the tiered storage as well. What else can we do with the calculator? Well, we can actually predict the minimum type, size, and number of brokers for Kafka. Thank you. So again, this is a bit sort of, there's a lot of assumptions around this calculation, but you will notice that it does predict an increase in the number of brokers from the local to the tiered cluster. Now, these are all the minimum numbers. You may already have that number, so you may not need to increase the Kafka cluster size or not. So you still really need to do some benchmarking, but we are thinking of adding to the performance model and increasing CPU, and adding CPU as part of the model as well. So eventually it might become a more holistic model of Kafka performance. Finally, the other interesting question people ask is how much storage do you need for the local versus remote and different types of splits. So this is just assuming 1 day storage in total for both use cases, but reduced for the remote one where you've got 1 hour on the local storage and 1 day for the remote, one hour for the local storage and 1 day for the remote storage. And that's quite a big reduction in storage that you need. And also a big reduction in, or an increase in savings, so about 7 times the savings, which is good. So there is actually a benefit of using the Kafka tiered storage. So another potential use case relating to the examples we've looked at is, what if you just want a lot more data to be retained for a lot longer? So what if you want to increase the amount of data to a month's worth of data? Well, then obviously you're going to need a lot more storage, but it is primarily S3, which is cheaper. So potentially up to about 10 times cheaper using the S3 storage rather than the local storage for that amount of data. So even though, I mean, the cost still goes up, it becomes a bit more practical to have large amounts of data if that's the use case that you have in mind. So just a few conclusions. Thank you, that was good timing. Try it out. That's how I got this talk, was trying it out myself, giving it a poke and seeing how well it worked in practice. We've got a 30-day free trial of developer-sized Kafka brokers that you can check this out on. There's potential cost savings and there's cost performance trade-offs as well. A few things to watch out for. Turning tiered storage on for existing topics with lots of data may cause some overhead for a while. S3 buckets are not automatically deleted if the cluster is deleted. You have to do that manually. But there may be some really interesting use cases which use more data with longer histories and different consumer behaviors that could be supported by tiered storage, essentially using Kafka as a database, which people have talked about for a while. There's limitations, but you can certainly store the data for longer, which may open up some interesting use cases down the track. And to scale the remote workload, you may need to have more partitions when writing the data to remote storage in the first place, more consumers and resources, and a bigger cluster potentially for more CPU. But now it's easier to do that as a cluster CPU and storage are independently scalable. So that was sort of the whole design goal of Kafka tiered storage. And that's it from me. Thank you. That was good timing. You can check out some more detail on this topic and more on my blogs there. And that's my LinkedIn QR code if you want to keep up with what I'm up to and things. I don't know what I'm doing next. If anyone's got any cool ideas for what to do around the Kafka streaming space, come and have a chat to me afterwards. So thank you very much.
Thank you.
Oh, there's a microphone. Hi.
Does Kafka allow you to loosen the ordering guarantees? And if so, shouldn't that improve your latency?
Loosen them. Sure. Yeah, I mean, the ordering is only guaranteed per petition, essentially. So if you want to do weird things with the ordering, there's actually a new type of Kafka consumer called the Kafka parallel consumer as well. That allows you to process records in a number of different ways compared to the default Kafka, including by key, which isn't sort of one that's provided out of the box for Kafka. So you have a look at the Kafka parallel consumer. That's quite cool. It's a
By key is
multi-threaded.
still ordered, it's just a different order.
Yeah. So it's a multi-threaded Kafka consumer. It's a lot more flexible in terms of the ordering and concurrency as well. So yeah.
Thank you. It's a very informative talk.
Thank you.
Was there in the back? Oh, that was you. Sorry. Yes. Thank you.
I just came to front
Yeah.
to save the time. I have seen one thing that when you have the backup, like from the local storage to the remote storage, there is a pipeline created. Like that duck was after filling that certain level, it will be backed up, right? So is there any downtime required for that, or it is asynchronously
No,
done?
no, it's just magic and automatic. So essentially the records are transferred to remote storage almost as soon as they can be. So essentially once the local segment is closed, which is a configurable size, the segment size in Kafka, then the remote storage part of the system gets hold of that segment and decides when it's going to write it to remote storage. There may be some delay at that point because it's asynchronous, and there's a lot of tunable parameters in the remote storage component, which allows you to work out how much data you want to be able to shift to the remote storage tier.
Is there any message maybe destroyed or maybe deleted in between the transfer between?
Oh, sorry, I missed that. Could you say that again?
Any loss of messages will happen between that delay?
No, it's got the same message delivery guarantees as Kafka intrinsically. So it'll it makes sure that all the messages are delivered, and there will be a local copy as well. So.
Okay.
So the other slightly weird side effect, which I hope people picked up on from this, is if you've got a, say, replication factor of 3, you'll actually typically have a lot more than that because of the storage and the records being in remote storage, because they are replicated anyway in S3. So I'm not recommending this, but there could be some use cases where you may therefore want to reduce the RF factor in your local cluster to less than 3. I don't think we recommend that in practice, but I can see people doing experiments with that.
Okay.
So,
Thank you.
thanks.
Thank you.
Thank
Any
you,
more?
everyone. Thanks.